Hello class, in this video I'll be showing you an application of Extrema that involves finding an optimal solution. Let's begin. A farmer has 2,900 feet of fencing. They want to enclose a rectangular field bordering a river with no fencing needed along the river. What is the maximum area that can be enclosed? Part A asks to define the variables. We will let x be the length of the side parallel to the river. And we will let y be the length of one side perpendicular to the river. Part B. Create the constraint function and solve for one of the variables. The constraint is the fact that the farmer only has 2,900 feet of fencing. To create the equation, I'm going to draw a picture. In this picture, I drew the river. The two sides perpendicular to the river are labeled y, and the side parallel to the river is labeled x. Since the farmer has 2,900 feet of fencing, we will have 2,900 is equal to x plus y plus y. So 2,900 is equal to x plus 2y. And since the coefficient of x is 1, I'm going to solve for x. So we have x is equal to 2,900 minus 2y. Part C, create the function that will be optimized. We want to maximize the area that's going to be enclosed. The area of a rectangle is length times width, so the function to be optimized is a is equal to x times y. Part D, create the objective function and find the domain. We know that a is equal to x times y. I'm going to substitute 2,900 minus 2y in for x and create a function of y. That will look like this. And now I'm going to distribute the y. So the objective function is 2,900y minus 2y squared. Now to find the domain. The side lengths must be greater than 0. So the first side length in the objective function is 2,900 minus 2y. That must be greater than 0. This implies that y must be less than 1,450. The other side length in our area formula is y, and that too must be greater than 0. So the domain is the open interval from 0 to 1,450. Now to find the critical numbers of the objective function. To find the critical numbers, I'm going to start by taking the derivative of the objective function. That will look like this. Next, I'm going to set the derivative equal to 0. That will look like this. If we subtract 2,900 from both sides, then divide both sides by -4, we will get y is equal to 175. Since 175 is in the domain of this function, we can conclude that it is a critical number. Part F. Verify that the critical number is the location of the optimal solution and identify the optimal solution. To verify that the critical number is the location of the optimal solution, I'm going to use the second derivative test. The second derivative of the objective function is -4. If we evaluate the second derivative for when y is equal to 175, that will equal -4, which is less than 0. Since the second derivative when y is equal to 175 is less than 0, there is a relative maximum at y is equal to 175. Now to identify the optimal solution. So the maximum area possible is 1,051,250 feet squared. And we are done.